this video we're having a look at how to determine the roots of some basic polynomials. We'll also have a look at the connection between the complex conjugates of those roots. In this first example we're going to solve the quadratic equation x squared minus 2x plus 2 equals 0. Now a basic process for solving this could be to factorize the quadratic equation and then use the factors equal to 0. But this one isn't going to solve using real numbers. So what we need to do is try another process. We could go through and use a quadratic formula, or another process we could use is to complete the square. Using this process, the first thing we'll do is form a bracket with x, and then we'll halve the coefficient of x. So our bracket becomes x minus 1 all squared. And that accounts for the first two terms in our quadratic expression. We then subtract the square of the number in the bracket. So in this case it's minus 1 squared, and then we add the constant at the end. Simplifying that, we get x minus 1 all squared plus 1 equals 0. What we then do to solve for the x is to remove the 1 and take it to the right hand side, so it becomes negative 1. We then remove the square on the left hand side, so we have plus or minus the square root of negative 1 on the right hand side. That's introducing an imaginary number, so the square root of negative 1 is I, and then we get x is equal to 1 plus or minus I. And you can see here, based on the completing the square method, that we're going to get conjugate roots because we are taking a positive or negative of that square root of negative 1. So that 1 plus I has a conjugate of 1 minus I purely because of the process we use with completing the square. And that also follows with the quadratic formula. You can see with the quadratic formula that we've got plus or minus the square root. So the square root is where the imaginary number will occur. So based on this, any solution which is complex will also have its complex conjugate as a solution because of that plus or minus in front of the square root sign. Now let's increase the degree of polynomials by 1 so that we're looking at some cubic functions. And we'll have a look at some basic situations in terms of roots of the equation. So we can see that the graph may intersect the x-axis at one point, it may intersect at 2 points, or it may actually go through and intersect the x-axis 3 times. But in each case it will always intersect the x-axis once, and that's true for any polynomial which has got an odd degree, in other words a cubic or a power of 5, etc. So what does that mean with respect to the factor theorem? Well, what it means is if it does intersect the x-axis, in other words there is a value of a such that the function at a equals 0, then that means that there is one linear factor. So that's significant for a cubic. It means our cubic expression can be factorized such that we have one linear factor and another factor based on a quadratic expression, which could be factorized further to give us real solutions, or it may be such that the solutions are complex conjugates of each other. Let's increase the degree of the polynomial by 1, so our highest power here is now 4. Now to go through and solve this problem we need to factorize, but we don't have a quick method to factorize a polynomial of degree 4. What we can do is use the factor theorem to find possible solutions for f at x equal to 0. So the first thing we'll do is we'll substitute in some basic numbers. So if we substitute in 1, we find that the solution will come to a value which is non-zero. So we'll try another number, in this case x equals negative 1. If you go through and check the calculations for yourself at this point in the video, you should find that after substitution we get a value that does equal 0. This is significant because it means that x plus 1, so the opposite sign to negative 1, x plus 1, is a factor of this polynomial. So we'll repeat the process again and try and get down to a stage where we're simplifying this expression into separate linear factors. So let's try another x number. This time we'll try x equals 2. Again, it would be wise to pause the video and check to see that you agree with these calculations for yourself. Given that the result is 0, we can say that x minus 2 is another factor of this polynomial. We can now write f at x as a product of x plus 1 in one bracket, x minus 2, and some quadratic expression so that we achieve our power of 4 for the overall function. What we are trying to do is find the roots of this polynomial. So what we need to do is examine our quadratic expression further, and we can do that by evaluating the product that's in brackets. When we multiply those brackets out, what we do is we get an expression that we can then equate to our original polynomial. Again, it would be wise to check here to see that you agree with the algebra in this process. First of all, we multiply out the two linear factors and simplify that expression to form another quadratic expression, x squared minus x minus 2. In the next multiplication process, we'll multiply x squared from the first bracket with everything in the second bracket, and we'll show that in red. Then we'll multiply negative x from the first bracket with everything in the second bracket, and we'll show that in blue. Then we'll multiply negative 2 from the first bracket by everything in the second bracket, and we'll show that in green. To make the simplification process easier, we'll identify like terms. So we'll give a horizontal line for the term with x to the 4, a squiggly line for terms with x cubed, a double line for the x squared, a little cross through it for the terms with x, and then the constant term will use a squiggly line. So what we'll now do is we'll mix our like terms together to see if we can simplify. We can see that we've only got a single term with x to the 4. That's ax to the 4. We can mix the two terms with x cubed by writing them as b minus a multiplied by x cubed. Likewise for the x squared, we've got c minus b minus 2a, that's all multiplied by x squared. And then for our x terms, we've got negative 2b, take c, and that's all multiplied by x, and at the end our constant minus 2c. What we can do now is match up our like terms. We can see with the x to the 4 term that the coefficient a matches the coefficient 1 in the original equation, and likewise the constant c at the end will equal 2, so that 2c is equal to 4. From there you can do your own algebra to find the value of b, and it turns out that in this instance, if you go through and use the coefficient of x cubed, you can find that b is equal to negative 2. Now to find the roots of our original function shown here in black, we can use the factors to help us. And we'll have a look at the quadratic expression first. Now if you remember, we solved that equal to 0 right at the start of this video. We can also see that the coefficients of the polynomial, in this case the quadratic, are all real. This will mean that it could have all real solutions, or if there are complex solutions, for any complex number, the conjugate will also be a solution. So going through this process quickly, we can see that our solutions will be x equals 1 plus or minus I, and we also have two linear factors, which give us solutions of x equals negative 1 and x equals positive 2.